All right, now in this next one, as we apply our idea of indefinite integrals and the net change theorem, we're looking at a particle, actually two particles that are moving along the x-axis. So I'm just going to read through. The velocity of particle p is at time t is given by some velocity function, sine of t to the 1.5 for t from 0 to pi. We know that at time 0, our particle is at position x equals 5. Our second particle, q, also moves along the x-axis. The velocity of this particle at some time is given by a different function, still 0 to pi, and at time equals 0, the start, we know that our particle q is at position x equals 10. So find the position of the particles p and q at time t equals 1. So we're given the velocity. Now we recall that the position is the antiderivative of velocity because velocity is the rate of change of position over time. So we can take this, I've got down here already prepped, position is the antiderivative of velocity. So if we want the position of particle p, then it's going to be the antiderivative of that particle. Ooh, I've also got plus c, that's our starting time. So our position is going to be this integral from 0 to 1 sine of t to the 1.5 dt plus 5. That plus 5 gets us that initial position. So the integral itself tells us our displacement, and we want that displacement relative to 5 where we started at the beginning. We also want to find the position of q at time equals 1. So similarly, over to the right side, we've got our position function. It's going to be the integral from 0 to t of our function plus some constant t. So when we evaluate for time equals 1, we're going to take the integral from 0 to 1 of that function t minus 18 multiplied by 1.5 to the t dt plus our initial value. So this is our displacement, and then we've got our initial value. So it's just a matter of put this into the calculator. We've talked about that before. I'm gone over to Desmos on the right side. So looking at this, I've got this evaluated already typed in there for me. And so we've got position of p at time equals 1 is 5.371. And the position of q at time 1 is, we have negative 9.585. Now, AP exam, we need at least 3 decimal places if we're going to round or truncate. Now, do we have any units? We have no units are given, so we don't know if this is meters, feet, time, if this is hours, whatever. We've got the positions relative to 0. So we're going to say that those are our starting positions. We've given the velocity function, and the integral, the antiderivative of velocity, gives us our initial position. So there's part A. Let's take a look at part B. Are those two particles, p and q, moving towards each other or away from each other at that time 1? So let's take a look at that. We know that at time 1, q is at negative 9.585. We know that at time 1, let's, what did I do there? Oh, no. We've got p is at 5.371. So I put this relative to 0 on our x-axis. We can see that at the start, q is on the left, p is on the right. So are they moving towards each other or away from each other? If they're moving towards each other, p would have to be moving to the left. Ooh, the velocity would have to be negative. If q is moving to the right, well, that velocity would have to be positive. So we need to test or find the velocity at that given point. So for part B, I'm going to evaluate our velocities for p and q at time equals 1. So I've gone over to the calculator here because I don't know 1 to the 1.5. That's a lie. Sine of 1. Let's find out what that is. Sine of 1 raised to the 1.5 is, we've got 0.841, and the velocity of q at times 1 is negative 21.25. So negative cues us in that q is moving to the left. Positive 0.841 for p is telling us that our velocity is positive. P is moving to the right. So because of the relative positions of p and q, q is further to the left and moving to the left, p is further to the right and moving to the right, they are moving away from each other. And so this would be our explanation, and we would put this into the words based upon the locations and the velocities. There's our part B, moving towards each other or away from each other. Let's take a look at part C. Find the acceleration. Ooh, acceleration is the derivative of velocity. So we want the acceleration of particle q at time equals 0, and then is the speed of the particle increasing or decreasing? Well, we know the velocity of q at time equals 1 is negative 21.25. So what we're going to do is we're going to find the acceleration. That's the derivative. Look at this, t minus 18 multiplied by 1.25 raised to the t. That is product rule. So derivative of the first, I've got 1, okay, times 1.25 to the t. Add to that t minus 18, yikes, t minus 18 multiplied by, okay, exponent rule is going to be the common divided by, nope, I'm thinking antiderivatives, multiplied by the natural log of our base, natural log of 1.25. So we want the acceleration of q at time equals 1. So when I go over to my calculator on the right, we know our velocity, our acceleration is negative 3.492, whatever that is, a distance per time unit squared. Now, speed, increasing or decreasing. Our velocity is negative, and then we are increasing in the negative direction. So because the velocity and acceleration have the same sign, both are negative, the speed is increasing. Speed is our magnitude. Like if we were thinking about this, our velocity is negative, but it's getting more negative. So if we're to graph our velocity, it is getting further away from a velocity of 0. And lastly, let's see part D. Find the total distance traveled by particle P over the time interval 0 to pi. Now, total distance, well, the integral tells us our displacement. So we're going to need an integral, and that's going to then find our displacement. Now, total distance is all the positive. Now, if I just look over on the right side, there's the graph of that function, sine of t to the 1.5. Sometimes we're moving in the positive direction. You can see from 0 to maybe 2 something. And then as we approach pi, we're going to have a negative velocity. So we're going to be moving to the left. So what's happening here is we would be having the area, the integral, just on its own, would be that net change. We're moving farther to the right with that green section and then to the left. We found the displacement relative to our starting point, but we want the total distance traveled. Total distance, we don't want that negative area. So what we're going to do is we're going to take the absolute value, and that's this integral expression that I've written over on the left side. What that does is it takes our curve and flips that negative, that leftward motion, to the positive. We're going to have the same area, and you can envision looking over at the graph on the top right, that area below is now going to be reflected above the curve, and we have that total area. That, with the absolute value, is going to be our total distance. And now I can evaluate that in the calculator, plugging that into the calculator. I'm not going to differentiate that by hand or integrate that by hand. And we get 1.931 total meters or feet or whatever it is traveled. There we go.